Bismillahirrahmanirrahim. Now we continue on chapter 2 on functions. Look at the definitions given. Fx is a function of x if there is a procedure by which each value of x determines a unique value of fx. The set of all permissible values of x is called as domain of the function, and the set of all corresponding values of fx is called the range. So for any functions given, we want to identify to find the domain and also the range of the function. So if it is a function, any value that you plug into the function of fx, okay, we will plug the value of x and then produce the value of fx. Okay, input of x and then the output of fx. And it must be one value unique. Okay, so let's see example 1. Okay, example that we have here is a function of x plus 1. The functions of x plus 1 is a linear function because you can see that here the x is to the power of 1 linear. Okay, x plus 1. So let's say we want to find the domain and also range for this function. Okay, if it involves most of the problem involved with x to the power of 1, so the domain can be all real numbers. Okay, why it can be all real numbers? So maybe we can sketch the shape for this graph. So the simplest way for you to sketch any graph, okay, especially any linear function, is we can identify the value of x and also y or fx, where x is 0 or y 0. Then we can find the respective values. If x is equals to 0 here, then obviously your fx should be equals to 1. And where your fx is equals to 0, okay, this is 0, so that x will be equals to negative 1. Now let's plot the values. It is x 0, fx is 1, so it should be here. And then you have 0 and negative 1. Okay, 0 and x is negative 1, and here is 1. Okay, so this is the graph. So we can connect these two coordinates. So this is the graph of x plus 1. So as you can see, this is for x values. It can have all values in the range of real numbers. Okay, on the real line, okay, this coordinate, okay, this line can cover everything from here until here, right? Okay, meaning that from the values goes to negative infinity and also to positive infinity. Okay, so from that we know that the domain for f should be equals to x elements of real numbers. Okay, or real numbers, or we can also write in terms of interval notations of negative infinity until infinity. Okay, that one is for the domain. Now we want to identify the value of range. Okay, range will be all the values as the output in terms of fx. So it is the graph. When we check the graph here, okay, this one, okay, the graph also the output of that, when we put any values of x, we can always find the values of fx. So let's say we replace with anything here. Let's say we have negative 2, okay, you go somewhere here, then you can get one values of that. Okay, so this one you can get the answer of fx. And if you plug in for any values, then you can always find the value of fx. Okay, so that shows that the range of f this range of f also equals to real number. Okay, the elements of fx should be the elements of real number. So it can also be written as negative infinity until infinity. So what we can conclude here, for any linear function actually, we can find the domain and range values as simple as all values in the real number from negative infinity to positive infinity, unless if you have rational linear that involved with the rational function. That is another case to consider. Now let's continue with the second example. Okay, example 1, second numbers. So it is the graph of the absolute value x plus 4. Okay, as you can recall, okay, the graph of the absolute values, it is in terms of V shape. Okay, like this, right? Okay, this is the graph of absolute values. So all the fx values should be positive, right? Okay, this is goes to positive infinities. Okay, so this one we have x plus 4, so the shift of the graph should goes to 4 units to the left. Okay, so it is negative 4 here. Okay, because if we replace, okay, the values of fx is equals to 0, so fx is equals to 0, then we will get for x plus 4. Okay, then your x should be equals to negative 4, right? Okay, so this graph should be at negative 4, and then also we'll cut the values of when your x now is equals to 0, so fx is also 4, so it should be at 4 and negative 4. So this should be the shape of your graph for x plus 4 absolute values. Okay, so for this one we can identify the domain. Okay, domain of that, it can be all values within negative and also positive infinity, right? So the fx is still the elements of real number, or in terms of negative infinity, and the range of f. Okay, so we are going to check where is the graph. So the graph just cover from the positive values, so it is here. From the positive value, this is at x-axis. So at this x-axis, y value should be equals to 0. So the domain of, the range for this function should be from 0, okay, from this one, the line, until positive infinity. So it should start with 0 included until infinity. Now we'll continue with example 3. Okay, so the given function is now 2x plus 1 over x minus 1. So that you can see here, this involves the rational function. Okay, so the domain of f given is x elements of real number, but x cannot be equals to 1. Okay, why? This is the conditions that we have, because we need to identify the value of the domain based on the denominator, because this part will contribute to the function to be defined or not. So the denominator x minus 1 equals to 0, so that x cannot be equals to 1, right? Okay, so this is the condition. When your x is equals to 1, 1 minus 1 here, meaning that you are going to get it over 0. So this is the undefined conditions for any rational. Okay, we have discussed the idea of rational function or rational numbers before. Okay, so the values of denominator cannot be equals to 0. Okay, so this is the domain. It can be any value except for 1, and in the interval notation we can get negative infinity, 1, or okay, 1 infinity. 1 is not included. Okay, why for the range for these values, it is all x elements of real number again, but fx cannot be equals to 2. Okay, so this is the notations for the range. Okay, how can we decide this is the range with the exception for the values of 2? Okay, we can check this by having the inverse kinds of function, finding the inverse for this function. Okay, so we have the remark here. Let's check the remark first, then we will go with the step of finding the inverse. Later on, actually, we have a special subtopic, okay, focus on the inverse also. So remark here, the range of the domain of the range of the function of f is equivalent to the domains of its inverse. Okay, so indirectly, when we can find the domain, okay, domain of the inverse, it is actually the range for the function. Okay, so now let's check on how can we find the inverse value for this function. Okay, so originally this is the functions that we have. Okay, 2x minus 1 over x minus 2x plus 1, sorry, over x minus 1. Okay, so we will let one values of y equals to all the functions that we have. So we are going to rearrange the function as the final step shows x as the subject of the equation of the function. Okay, so yeah, I think this one you can try to simplify. So this one move here, so you can multiply, and then here you are going to expand. So xy minus y is equals to x plus 1. So that here we have, okay, we have to collect one variable. So here is x, so that this is 2x. Okay, we move from here, so that we are going to move that 1, okay, 1 is there, so negative of y will become positive there. So we can factor for this x, so left for y minus 2, and then we can find the x as the subject now. It is 1 plus y over y minus 2. Therefore, this is the value of inverse. Inverse for the function equals to 1 plus x over x minus 2. So when this is the inverse, you can look at the value of denominator part here. So as x minus 2 cannot be defined when it is 0, so the x cannot be equals to 2 here. So this one is the range for this function. As you can see here, this is the graph for this function. So when we look at the shape of the graph, it is actually represent where the values of the x and y cannot be equals to. Okay, that will be the mark, or in the graph we call it as the asymptote, the line of asymptote. So this one, x cannot be equals to 1. Okay, so we have a line, x is equals to 1 here. Right. Okay, as x equals to 1, this one, your graph can't touch the line. And for the range, it is fx cannot be equals to 2, right? Okay, so we have another horizontal line of the asymptote here as x is equals to 2. Okay, so you can try to sketch, okay, plot the graph replacing the values. In details, this one we are going to use the idea of limit actually. But we can always plot or sketch the graph by predicting the values of x and y, especially for the intercept. Okay, I mean the x and y intercept. So let's say we want to check on x and fx. Okay, as x goes to 0 and fx also 0. So we'll check for the intercept first. If x is equals to 0, okay, when your x here should be equals to 0, then your fx or your y is equals to negative 1. And if your fx is equals to 0, okay, so the whole equation equals to 0, meaning that 2x plus 1 equals to 0, so that your x will be negative 1 over 2. Okay, so this is the intercept. As you can see, it is on 0, negative 1. Okay, so this part, and also negative 1 over 2 and 0, this one. Okay, so we have these two coordinates. We can connect in these two coordinates, okay, because we have the intercept, so it should start from here and then goes until that, right? Because the graph can only be approached, okay, approximate to the intercept, okay, sorry, to the asymptote here, okay, the line of y equals to 2 and x is equals to 1, but it cannot touch the graph. Okay, and for this side, okay, let's predict the values. Here we have 1, okay, maybe we can predict the values when the values of x is equals to 2, for example. Okay, if x is equals to 2, then 2 and 2 we got 4 plus 1, it is 5. 5 divided with 2 minus 1, it is 1 positive. Okay, so that coordinate should be 2 and negative 5. So it is here 2, and if we put somewhere here as 5, so okay, so maybe we can put it here, the value of 5. Okay, so that here is the coordinates, right? Okay, so we want to check the values as x goes to this side, right? Okay, 3, 4, 5 and so on. Okay, maybe we can try to what you call the plug in the values of x is equals to 5, let's say. So when x is equals to 5, 5 times 2, 10, 10 plus 1, it is 11. 11 over 4. Okay, so that we have the coordinates of 5, okay, and 11 over 4. So 11 over 4, that it is actually equals to 2.75. Okay, 2.7 something here. So it should be somewhere here, right? It is 11 over 4. Okay, so when we have these two coordinates, we can connecting these two values, and this is the shape of the graph. So when it involves the rational function, okay, we have these kinds of shape of graph. Depends, maybe sometimes you have the shape like, okay, here and here, depends on where is the asymptote. Okay, so how can you identify the asymptote? It is from the values of the function cannot be equals to, depends on the denominator part. So we are looking for these values, denominator part.